Thank you very much for the introduction. Okay, let me start with a simple example. At least that's how it kind of looks like. Okay, so an example of a diffusion processing pipeline and analysis combined looks something like this. So you've got data acquired, you do a lot of processing, pre-processing steps, you choose some model, and then you get to this stage, some analysis framework to get your statistical inferences. It looks straightforward, but in practice, it's a lot more complicated. Okay? And I'll just give you an example of how things work in my lab. So that's me, sitting in my office, and here's a handsome and rich Dr. Bob again, and he steps into my office, and he says, "Hi, Alex, I want to do some diffusion MRI on a patient with this rare disease. Has never been done before." Okay, so that's kind of how it starts. And obviously he's trying to lure me into doing a lot of work because he thinks, you know, things are publishable and very exciting. But I highlighted this area here, right? So do some diffusion MRI. I mean, you can't be more vaguely than that, right? So what does he want to do? So, you know, one of the questions I had, okay, what do you want to scan? Because we're kind of biased towards the brain, but nowadays we can scan even kidneys. You know, there's actually a power pitch on Thursday on doing diffusion MRI on the kidney or peripheral nerves, okay, sacral plexus, forearm nerves, or muscle tissue. Dr. Fruling will give a talk on this, I think on Thursday, if I'm not mistaken. So there's an entire, you know, field beyond the brain. Okay, so this is where I kind of start. What organ do you want to scan? And do you want to scan in vivo or ex vivo? Because that also changes the game, right? You've got more time, you know, motion is not an issue, so you can think of other sequences. So in a way, everything's interconnected, right? Here's an example of, you know, scanning ex vivo, so you can, you know, scan at a high resolution by trading in, for instance, you know, more scan time. But there are many, many more questions, and they're all interrelated. So when somebody comes up to me like, you know, we want to do this, then we need to actually address all these questions. But I think one of the first ones I tend to ask is, okay, how much scan time do you have? Because if it's somebody from the neonatal department and they're scanning, you know, young babies under, you know, sedation, then obviously, you know, you can't scan for 20 minutes there. So that is actually also tied down with the research question here at the top. So what is it actually that you want to do? You know, do you want to investigate some mean diffusivity measure, or do you want a full diffusion tensor or beyond the tensor? Okay, so these are very important questions, and it's all connected. I also want to follow up on a few recommended pre-processing steps that are, you know, always kind of required. Okay, so it doesn't matter which type of analysis you do, the following ones we typically do, and I'm not going to discuss number 3 and number 4, but I will provide some more details about the first two. Okay, the first one is correction for signal drift. So what you may or may not know is that if you're acquiring data with your, let's say, B0 images interleaved, then that signal is not constant. Okay, the scanner is not perfect, things are heating up, and the signal decreases typically. Okay, how do you correct for that? Well, that's actually trivial. And by the way, it's not just on the B0 images, it's also on the diffusion weighted images. So not just the non-diffusion weighted images, but also the diffusion weighted images. It's less obvious because the signal is already quite low, but I guess, you know, this B value range, you can still see the decrease, right? So to correct for that, you can simply fit a low polynomial to these non-diffusion weighted signal values, and then apply that trend that you just, you know, estimated to your diffusion weighted data, but all of them, also the non-diffusion weighted data. Okay, and this is, let's say, the first pre-processing step that we tend to do nowadays on our data. So you acquire data, and you apply this correction strategy. Okay, it becomes even more, let's say, relevant if you're acquiring data which takes a long time. So if you're acquiring hardy data with many directions, then this is typically something that you can observe this trend. So what's the effect? Well, so this is before correcting. And this is after. I'll just flick between them, so you might appreciate the difference. If you can't see that well enough, then let's look at the difference itself. And what I want to show you with this image is basically that the difference in FA is heterogeneous across the brain. Okay, so it's not just a global scaling as well on the diffusion data. For each voxel, it can be different. Okay, and because an absolute difference is, quite difficult to interpret because the FA value itself may be very low. Let's put it in perspective and look at the percentage difference. And in this case, with a signal drift anywhere around 10 to 15% or 5 to 10%, that order, more than half of the voxels can have an FA difference of more than 2%. Okay, so keep that in the back of your mind. That's also, similar to the order of magnitude that effects are typically found when doing group analyses. And then secondly, subject motion. I'll be quite brief here because it was covered by Carlo. One thing I want to mention is that diffusion data is not like fMRI data. It has orientation contrast in it. So if you look at this toy example, if I were to just naively correct for misalignment by using image registration, then maybe spatially now the data are back aligned, but clearly orientation information is not corrected. Okay, you can do that by rotating the B matrix. So here's an example on a real data set. So this is the contrast if the subject did not move. And let's simulate some motion and then look at the contrast. So it's the same diffusion gradient applied, but because of motion, you can clearly see now if we zoom in or highlight this area, the contrast is different. And this will obviously affect your diffusivity estimates. Okay, so you can here see some dodgy estimates of DFA in the splenium here. So what you should do is reorient the data, but then also apply the B matrix rotation. There was a question in the audience this morning, like should we wait for the next model? So I've just added a few slides as an intermezzo to show that we can already do some interesting things with models that we have. And I'll just emphasize this issue by showing you this image here. Okay, so this is a T1 weighted image, and I'm asking you, is there anything abnormal that you can observe in this area? Okay, so I asked 3 radiologists. None of them could see anything abnormal. Okay, but let's just look at DTI, color encoded map of the FA, and you can clearly see something abnormal here. Okay, so we're all aware of the limitations, crossing fibers, but still you see something abnormal here that we could not explain. Okay, we thought first maybe it's an artifact. Let's look at the residuals. Nope, nothing. Okay, partial voluming? Nope, no partial voluming. So in this case, the subject actually has some abnormality here. Actually, I can actually say who it is. It's Russ Poldrack. It's a famous neuroscientist, San Francisco, and yeah, you can clearly see some abnormalities here which you cannot detect on a T1. I just asked Chris Hess to have a look at this as well. Couldn't see anything. Okay, and maybe this top structure, he told me was it's not abnormal to actually observe this, but this middle part clearly is. And then you may argue, well, this is a healthy subject. This is an accidental finding. What about the clinics? Well, in this case, there was a child with learning disabilities, and they could not target where is this coming from, right? Until they actually accidentally looked at all the data they acquired, which also included the diffusion data, and again, something abnormal was observed here. I'm not saying it's necessarily related to each other, but at least for the parents, they could indicate like, well, we see something abnormal and it may be related to it. Okay, there's no causality per se. Okay, that was a quick intermezzo on DTI being already, a good model for some applications. And then there's all the different analysis approaches, and there's many. You can look at looking at a single voxel. If you, for instance, register your diffusion data to a T1 map and you annotate a region on a T1 because you may be very familiar with locations in a T1, then you can extract the diffusivity values. That's vanilla analysis, if you want. Okay, it's very simple, but it works. Then there's histogram analyses. Okay, so you're basically not specific anymore as to where in the brain you can detect a difference, for instance, between two groups. But at least you can be very sensitive if it's a global diffuse disease, for instance, if pathology is involved. You can also look at atlas-based approaches where you're transforming, registering data from an atlas to that single subject, and then warp the corresponding regions of interest to extract the diffusivity metrics from that as well. But I'll start, in this case, with one of the more popular approaches, which is tractography, and many of you are already familiar with that, but to the novice in the field here, let me give you a quick toy example here. So if we look at the diffusion data, and if we take the diffusion tensor as an example, then we can already piece together all these elements here, right? So we basically reduce the ellipsoid to its dominant orientation, and then it's a similar process like this cartoon example. You just follow and connect these discrete elements here. Okay, so here's the example for the data set. So we use seed points, as they're called, starting points, from which you then iteratively follow the dominant orientation in 3 dimensions until you meet some criteria like angular deviation or some diffusivity parameters have been met, like the FA becomes too low, etc. Well, this was actually just a wake-up call. I know many of you have a jet lag, so there you go. Refreshed. And obviously this is not Star Trek, but this is what a seed point would actually look like if it was traversing through this orientation field. Okay, and in practice we don't just sample one point or a few, we sample the entire data set. Okay, and then we end up with these spaghetti-like structures that you can see here. And apologies for the lame joke, Chris, but I once had a junior radiologist that came up to me and said like, "Oh, Alex, I didn't know these axons were that thick." Okay, so obviously we're not looking at axons. Okay, these are just representations of pathways reconstructed with tractography. Okay, the only reason why we provide these kind of shaded tubes is to be able to convey the architectural configuration more clearly, right? So in this example, looking at the Uncinate fasciculus, it's more easy to appreciate that you're looking from the bottom, basically, right? This is the temporal part, this is the orbitofrontal part. And the nice thing about tractography is that you could use it as a kind of, there's many ways that you can use it. One of which is, well, let's use that as our region of interest. Right? So that's a very popular approach. So basically people say like, well, I want to be more specific than just drawing a region of interest in a white matter region. No, I want to draw or extract the diffusivity properties of the entire tract. Okay? And this is something I typically use as a kind of disclaimer. We're not really looking at tracts here, okay? You could say tracts without the T, or fiber tract pathways, but anyhow, it's always an indirect measure. So we're not looking at a direct measure of, the underlying, pathways. And it's actually affected by many issues, okay? So I'll give you a few confounds, one of which is partial voluming. So at some point, we were estimating diffusivity properties, let's say the FA value from a tract. And then at some point, we thought like, okay, to what extent does size of a tract, provide a kind of confound related to partial voluming to the final estimate? So what we thought was, okay, we know that the edge of a tract typically has lower FA voxels, okay? A tract interfaces with, let's say, gray matter or CSF, the FA is low. And if you have a bigger tract, then you have less of these partial volume affected voxels pro rata. Okay, so absolute, you've got more, but pro rata, you've got less, because you basically have a ratio of radius versus surface. Okay, so the R in the denominator still says like, well, if you have bigger tracts, you've got less partial volume affected voxels that contribute to the low FA at the edge. Is that clear? Okay. So we thought, okay, let's put this to the test, right? Let's look at some structure which we can nicely model with, let's say, a circle as a diameter. So if you use our virtual scissors now, cut it open, look at the top, we can already appreciate visually that indeed the FA is higher in the middle than at the edge, so that's still no surprise. But what we then did was like, okay, let's fit a circle through this cross-section. It's an approximation, but still. And then correlate this with the FA value in that area, okay? And to our surprise, the majority of the variance explained was due to size, okay? So you have to keep in mind that the FA could be modulated by partial voluming, which was in turn co-modulated with size, okay? So the kind of take-home message here is that if you find a difference, let's say in FA between two groups, you may want to check whether volume, for instance, of that tract may have been a covariate not of interest, okay? And tractography is not perfect, okay? There's many issues, and to some extent I actually would prefer to look at these tracts like this, right? Because there's uncertainty, there's model uncertainty, there's noise, but obviously this is not really convenient to look at tracts. But I just want to raise awareness that these tracts, these pathways, they're not set in stone, okay? They're very dependent on noise, and in some area there's a lot of uncertainty, and in others there's less, and in regions where you do have a lot of uncertainty, you may suddenly jump to another bundle or whatever, okay? The model assumptions, you've already heard quite a lot about this. This obviously also affects tractography, right? So if you're doing DTI, on this data you get something like this. With another model, the same data, you get more specific information within each voxel in terms of different orientations. This also obviously has an effect on tractography. So if we look at that same data set and seed a few voxels in a mid-coronal section, then with DTI we typically see this U-fiber shape, okay? But with spherical deconvolution, we get something else, okay? I'm not necessarily saying which one is better. Let's, for now, say that it's different. And you need to be aware of that, all these issues play here, so. Another one, which is, also very popular, is tract-based spatial statistics. Okay, I just want to actually indicate this. It has been cited more than 2,000 times, so it's widely applied. So how does it work? How does tract-based spatial statistics work? Okay, so let's assume you've got your healthy controls over here and patients over here. What it basically does is press the right button and you get your result. Awesome. Okay, that's maybe partly can explain why it's so popular. It's very user-friendly. A lot of people use it. The only input it requires are the FA images. Okay, so it's a very efficient way of doing the analysis. Kidding aside, let me go into more detail on how it really works. So the first step is, if you got all the FA maps of your subjects, is to create a common template, okay, a common data set. Alternatively, you could use one of the predefined templates that is provided with the toolbox. The second step is to create a skeleton. It's basically a thinned version of an FA map where the FA was locally maximal. Okay, so it's in 3 dimensions, it's actually a sheet. Okay, and then from this skeleton, you basically back project to each subject to then find the locally maximal FA value for each subject again. Okay, so the idea behind this is that all these data, they should not be perfectly aligned. Okay, and this step corrects for this. And then the final step is to do your voxel-wise analysis, let's say with TFCE, and then you get your statistical inferences. But just like tractography is not perfect, TBSS is not perfect either. Okay, and in this paper, some of these limitations have been mentioned, and I'll go through a few of them. And the first one I want to mention is that a lot of people get confused because here's, Dr. Bob again, and he says like, hey, Alex, I really want to do a tract-based analysis. But then at that stage, it's not clear to me, does he want to do tractography or TBSS, which is a voxel-wise analysis? Okay, so that's kind of confusing. And indeed, technically speaking, a tract skeleton as presented in the paper, so this combination of two words, is misleading because we're not using orientation information. We're not looking at tracts, we're looking at FA values. So the orientation information from the diffusion tensor is not included to compute the tract, quote, quote, skeleton, okay? And you can do this even, from an image processing point of view. You can actually calculate the tract from the template and overlay the tract skeleton from this tract with the FA skeleton in white. Okay, and you can see while they have some similarity, they're definitely not the same. And this is kind of expected. Again, orientation information is not captured in the FA itself. The second one, I think, is a bit more fundamental, is that it may actually be biased with respect to the pathology that you're interested in, for instance, the effect of interest. So what I'm showing you here is a single subject with the skeleton overlaid. Okay? At this stage, the projection step is applied. Okay? So what happens is for each point on the sheet, on this skeleton, perpendicularly, the locally maximal FA value is found. Okay, so it says like, okay, in this area the FA is maximal. Great. So then indeed you can assume that there's anatomical correspondence. But what happens if you've got pathology? Well, in that case, let's just simulate some pathology. There you go. The FA typically drops. You see a lower FA value. But that means that if you do the projection step again, the locally maximal FA value may actually be in a different location. So the anatomical correspondence may be mismatched due to the effect of interest. So by design, you will not be able to find your effect of interest, potentially. Okay? So this is something to also be aware of. And thirdly, well, some areas are not really specific. If I ask you, what area is this? Is that part of the corticospinal tract? Or is it part of the corpus callosum? Well, there's no right or wrong here. Could be both, could be one, could be the other. And this is also one of the problematic things because you, again, have no information about long distance tracts, right? So if you have two pathways converging to each other, such as, for instance, the uncinate fasciculus, the orbitofrontal part, and the fronto-occipital pathway, they converge, right? So at that location, it may well be that the FA values of one subject are from the uncinate fasciculus, but from another subject, the same location is from the fronto-occipital fibers. And the same holds for many other regions, such as in this case the corpus callosum and the corticospinal tracts, which merge in this area. Okay? So this is also something to be aware of. But I guess the multi-million-dollar question is actually, well, if TBSS is not really tract-based, why the acronym? Well, who was the last author? That was Timothy Behrens, right? And who was the first author? Steve Smith. Timothy Behrens, Steve Smith. Getting it? TBSS. Okay? I know. It's pretty cool. A lot of sense of humor. Okay, finally, I would like to mention, so this is the final pipeline I'm going to discuss, which is connectomics, right? I'm pretty sure all of you must have heard of this, but just to be sure how it works, I will present in the following slides some more details about this. Okay, so the idea behind connectomics from a structural point of view is that we should not necessarily look at brain regions or even look at individual bundles, but look at more like the topology of the network that they form, how they are kind of interrelated to each other. And it works with a lot of techniques borrowed from graph theoretical analysis. Okay, so these are some typical jargon here. They talk of nodes and of edges. Okay, so these are the regions and these are, let's say, connections. And you see it everywhere, right? There's a lot of science on networks. Think of Facebook, the fact that that person suddenly pops up in your network as a potential friend. You're like, oh, I haven't seen him in 20 years and Facebook knows. Well, it's all this knowledge there gathered to provide you this information. You also see it in flight network information. There's a lot of knowledge there that we can borrow. Obviously, Lisbon is not that much of a hub, according to this magazine. But, so how does it work for the brain? Okay, so step one, we need to define the nodes. These are the brain regions. So in this case, I've used a free surfer parcellation example. Second step, well, we need to define the edges, okay, the connections, the brain connections. And you do this basically by including step one, which are the brain regions, and then basically find every combination of pairs of regions and see, are there any tracts, connecting them. Okay, so if you've got, let's say, 100 regions, then it's 10,000 divided by 2 number of possible, connections that you need to investigate. Okay, so this is quite an expensive, in terms of computational cost, procedure. And then the third step is to, well, actually define the connectivity matrix. Okay, so some measure that you could use to identify, brain region 1 is connected to brain region 2. And then you could say, like, okay, I'll call it a binary matrix if there is a connection, or you could use the FA or number of tracts. There's all these kind of measures from which you then compute, network properties and look at the brain as a whole, as a network. Okay, and there's an entire field of research on this. I think one of the grandfathers, or I'll say fathers, he's not that old, is Olaf Sporns, and you may want to look at some of his reviews there. But there are many challenges there, okay? One of which is, which diffusion MRI approach are we going to use? Okay, so in this case, I'm showing you some work from Kathy Ruddy, and she looked at the intercallosal or transcallosal connectivity of the motor network. And in this case, she used a spherical deconvolution approach to connect all these different areas, okay? But if you were to use diffusion tensor imaging, then obviously these guys, they can't be found. Okay, so is that it? Is it just more or less? Well, it's also a bit more complicated, because if you look at this one, primary sensory motor cortices, with spherical deconvolution you get something like this, but with DTI you get something like this. So you may say, like, okay, it's just a part of it, but if you focus on these pathways, also these pathways are different. Okay, so it's much more complex than just to say, like, well, DTI is a subset of the other techniques that can deal with crossing fibers. Okay. Another issue is, how do we define the connections, the edges, right? I mentioned, this measure here. Okay, the number of tracts, the FA of a tract. It's kind of, there's no decision made by the society. It should be this. And think of it, it's the same with, the flight network that I've shown. Obviously, Amsterdam looks like a hub here, but obviously these are all KLM flights. So if I've taken some Portuguese airliner, then obviously Amsterdam would be dwarfed by Lisbon. Okay? So it's very important to be aware that different choices can be made to actually build this network. Which brain parcellation approach? I mentioned that I used free surfer, but I could use other atlases. How many brain regions? 100? Only 50? Or like the anatomical atlas labeling, the AAL template, also very popular? Or maybe should I use every voxel? Or, so that's also something, kind of ongoing as where should we go? And there are many, many more issues. We haven't even discussed, what about the multiple comparison correction? Okay, I'm not going to dive into this now, but we all remember the early days of voxel-wise analysis in diffusion, right? Or even if in fMRI, it's still, debatable in many ways. It's Bonferroni, family-wise error correction, TFCE, there's, cluster approaches. Well, what about, network analysis? There's a lot of, hypotheses being generated. How do we correct for that as well? One thing I can say is that many peers of mine find that the artistic value is still higher than the scientific one. Okay, so it's kind of problematic, but again, it gives, there's opportunities to progress here. If you want to become more depressed, I can highly recommend the 25 pitfalls paper. There's actually a nice follow-up paper as well. A lot of fallacies that people have been encountering and doing. And And with these review papers, I would like to end my talk. I would like to acknowledge many of these collaborators. In particular, I would like to thank my team members. And actually, I forgot to remove Chantal Tax. She just graduated last week. She's now working at Kubrick with Derek Jones. And with that, I would like to thank your attention. I'm happy to take any questions.